Hello and welcome to today's lecture on broadband microstrip antenna. In the last few lectures we have been talking about broadband microstrip antennas, and we saw there are certain techniques to increase the bandwidth of the antenna. So, you can increase the bandwidth of the antenna by increasing the substrate thickness or by reducing the dielectric constant of the substrate, or we can use multiple resonator techniques. Now, in the last lecture we had seen how we can increase the bandwidth by putting the multiple resonators in the same plane. So, for example, if we have a one patch here, we put another patch here and we put another patch over there. So, there were three patches which were coupled to the radiating edges of rectangular patch, or we put three patches which were coupled along the non radiating edges. Then we looked into five patches which were coupled along all the four edges of rectangular microstrip antenna, and we saw that bandwidth can be increased from 10% to about 18 to 20%. Then we also saw that gap coupled circular microstrip antennas can be also used. Similarly, you can use other shapes also, you can use triangular, you can use hexagonal and other shapes also. Then we also saw that a U slot can be cut inside a rectangular patch. So, idea is that the resonance of U slot should be similar to that of the rectangular patch. So, if the two frequencies are close to each other, we can get broad bandwidth. Now, today we will look into the situation where instead of increasing the patch dimension in this thing here by adding another patches, so total dimensions are increased in the planar way, but now what we will do, we will put a patch here, then we will put another patch on top of that. So, this will be stacking of the patches. So, by increasing the total thickness of the substrate, or you can call it antenna, we can increase the bandwidth. So, let us just look at various configurations how we can increase the bandwidth by stacking the antennas. So, to start with, we will look at electromagnetically coupled configuration in the top. So, over here you can see these are microstrip line fed microstrip antenna which are rectangular or circular shape. So, here is a one substrate, on that substrate there is a microstrip line is connected. Generally this microstrip line width is chosen such a way that it corresponds to characteristic impedance of 50 ohm. Then we have a patch on the substrate. Now, there is no ground plane over here, the ground plane is only at the bottom side here. Okay. So, we have a ground plane, then a microstrip feed line and then a patch. Now, instead of a rectangular patch or a square patch, we can take circular patch, elliptical patch, triangular patch and so on and so forth. Now, over here there are two possibilities are there, that is that the substrate can be directly sitting on this here, or there can be an air gap in between. So, if there is an air gap in between, that would mean that effective dielectric constant seen by this patch will be relatively less, and that leads to the larger bandwidth. Now, there is also option that instead of printing the substrate on the top side, we can print the substrate on the underneath also. Now, this kind of a configuration is actually very popular in a sense that we can have on this substrate amplifiers or oscillators or mixers or power dividers, couplers and so on and so forth, and we can optimize this substrate parameter according to microstrip line. See, for microstrip line what we really want, the radiation from the microstrip line should be as low as possible. So, what we generally do it is we use generally a higher epsilon r substrate and a thin substrate, so that the fringing fields are relatively less. And here if we have air gap, we can also use another substrate of a low dielectric constant, so that the effective dielectric constant seen by the patch will be relatively small and the total height will be more, that would lead to a larger bandwidth. Now, there is another possibility is there, that is instead of having a microstrip feed line, we can also have a one microstrip antenna here, and that is being fed using let us say a coaxial feed in this case, and we can have another patch on the substrate. Now, patch can be printed on the upper side or it can be printed on the underside also. So, basic idea here is that now the bottom patch will be resonate at one frequency and the top patch will be resonate at some other frequency. So, there will be two patches which will be excited. Only one patch is being fed, other patches getting excited through the electromagnetically coupling, and that is why the name is electromagnetically coupled microstrip antenna, or in short ECMSA. So now again the patch shape can be anything, it can be rectangular, square, circle, triangle, and so on and so forth. So let us just see an example. So here is a example of two square patches which are put on top of each other. So there is a one patch over here which has a length L1, there is another patch which is put on the top substrate here which has a patch L2. Now many a times the option can be whether we put the patch on the top side or we put patch in the underneath. So I can just tell you some pluses and minuses. So if you put the patch on the top, then what it actually sees, it sees a larger thickness, and we know that larger thickness is good for the bandwidth, but then it sees relatively lesser dielectric constant compared to if the patch is over here, because now this patch will see one dielectric layer, then air, and then dielectric layer. So one needs to calculate what is the effective epsilon seen by this particular patch. But if this patch is printed underneath over here, then what happens, the top substrate acts as a radome also. So one can simply use this top substrate as a radome. So we do not need an external radome, and simply pack this antenna in some box which can be metallic from the side or can be a plastic box. So this is the one of the advantage of using the patch underneath it. Okay. So now what we need to do with is, let us say now we want to design a broadband antenna. So generally speaking, for a given bandwidth which we need to do, so divide that bandwidth roughly into about say 3 different parts. So at the lower part you design the lower patch here, and for the upper 1/3 part you design this patch over here. Okay. So generally resonance frequency of the top patch should be slightly more than the bottom patch, and gap between the substrate controls the coupling between the patches. Let us see an example. So here is an example of the different values we have taken. So we have taken a gap delta which is 0.1 centimeter, 0.3 centimeter, and 0.4 centimeter. So this is the gap between the two substrates, and we have taken the two substrates as same, which has dielectric constant epsilon r equal to 2.22, and individual substrate thickness is 0.159, and tan delta for this case is 0.001. Now for gap for air, tan delta is equal to 0, and here are the examples where we have taken L1 equal to 2.5, L2 is also 2.5. Now x is very close to the edge, you can see that 2.5 is the length, so half of that will be 1.25 centimeters. So one can see that 1.1 is very close to the edge there. So let us see what is the result and response for 3 different gaps. So we can see here there are 3 different curves are given. So one curve which has a smaller loop, then a little larger loop, and then this is a much larger loop in the Smith chart. So much larger loop corresponds to the lowest air gap, which actually mean that the coupling between the bottom patch and the top patch is very strong. So if there is a stronger coupling, then the loop size will be much larger, and as the gap increases, we can see that the loop size is reduced. As the gap increases further, the loop size is reduced further. Corresponding to this, now one can see now the VSWR plot here. So one can see for the larger loop, VSWR is less than 2 here and less than 2 here. So you can even think about that this antenna also acts as a dual band antenna. So we have a one resonance here, another resonance over here. But for broadband, we can actually see that both these loops are within VSWR equal to 2 circle. Now since this loop is relatively smaller, so number of frequency points within VSWR2 circle will be relatively small, and for here number of frequency points within VSWR2 circle will be large. So we can see that this is for that smaller loop which is for delta equal to 0.4, and this is for larger loop for which delta is 0.3, and we can see that this is a larger bandwidth. So, for this particular case here we can see that the bandwidth is about 816 megahertz, which is 20.6% bandwidth. So, we can see that it is a much larger bandwidth and can be used for design of various antenna. This is the case for 0.3 centimeter, and correspondingly here one of the nice thing with this configuration is gain is relatively flat over the bandwidth, and the gain is about 8.3 dB at 3.95 gigahertz, which is approximately the center frequency. Now, even this smaller loop size is sometimes useful. One can actually see that this is the response here. So, this loop here which is the peak at this is actually slightly below 1.5. So, many a times antennas are required not to have just VSWR less than 2 bandwidth, but sometimes it is required that we need VSWR less than 1.5, and I will tell you the reason. VSWR less than 2 implies 11% reflected power. VSWR less than 1.5 requires about 4% reflected power and 96% transmitted power. So, many stringent applications do require where we want VSWR to be less than 1.5. So, this can be optimized even further if one requires, because you can see that this loop is slightly outside the 50 ohm point. So, slightly this can be shifted this side, and that can be done by slightly shifting the feed point towards the edge. So, the whole curve will shift from here to this side. So, a little bit optimization can be done also if VSWR less than 1.5 is required. So, now let us just see one practical application. This antenna we have designed it for GSM 900 band. Okay. So, GSM 900 band is from 890 megahertz to 960 megahertz. Now, for this particular application we did not choose any dielectric material because the requirement was for low cost antenna. This is actually specially for cellular band, and for cellular application generally telecom industry prefers a very low cost antenna to save overall cost, and yet they want a rugged antenna also. So, we actually chose metallic plate instead of using a dielectric thing, and metallic plate can also handle much larger power. So, power requirement was not much. We had a major challenge was how to suspend metallic plate in the air. So, what we did that instead of suspending in the air, see if it is a dielectric substrate, it is not a problem. You just take a dielectric substrate, we have a ground, and if you have another dielectric substrate, we can put 4 screws at the end and we can support that. But here we have a metallic plate. So, what we decided, we supported this 2 metallic plates here by using a shorting post at the center. You can see over here. So, let us just go step by step here. So, L1 is 15.2 centimeter, and corresponding to L1 this height is delta 1, which is equal to 1.1 centimeter, that is an air gap, and this metallic plate is chosen of a thickness of 2 mm. Okay, so that it becomes very rugged and also it can handle a very large power also. The top patch is length is L2 is 12.8 centimeter, and the air gap between the two is now 1.3 centimeter. Basically, this gap has been chosen such a way so that the loop size is optimized, and feed point is again very close to the edge, which is at 6.5 centimeter. So, you can see that this is the feed point over here. Okay. And the ground plane size is taken as 24 centimeter. So, it is basically everything is square. So, all top, middle and the bottom ground plane, they all are square. So, these are the dimensions which we had chosen. Now, just to tell you, so in order to do the design, what we need to do it is, so we know frequency 890 to 960. So, corresponding to the lower band, this length was decided, and we chose the gap here so that we can realize the larger bandwidth to meet the requirement. So that is how we do the design here, and since air has epsilon r equal to 1, so effective dielectric constant is equal to 1 for this case. And just to tell you how to take care of the thickness 2 mm. So this is the thickness is 2 mm here, and what you can do that you can account for the thickness by adding to this length additional 2 mm on this side and additional 2 mm on this side. So L1 will be nothing but instead of 15.2, to account for this finite thickness of the plate, we can actually say 2 mm is equal to 0.2 centimeter and 0.2 centimeter on this. So effectively you can think this is 15.6, and then to account for the fringing field, we have actually told you that fringing field can be accounted or approximated as delta L equal to h by square root epsilon r. But I had also mentioned that the maximum value of delta L should not be taken more than 0.9 h. So we know h here, you multiply that with 0.9 and effectively take the length which accounts for the thickness of the plate, and that will then determine the resonance frequency, and this delta 2 basically controls the loop size in the impedance plot. So this antenna has been fabricated, this is the photograph of the fabricated antenna, and these are the measured results. So one can actually see that the measured bandwidth is from 872 to 1000 megahertz. In fact, this is the general thing which I generally do. The bandwidth requirement for this is 890 and the lower is 872. So we have a margin of about 18 megahertz, so that is about 2%. The upper one for this is 960. We have a margin of roughly about 40 megahertz here. So idea is that there can be tolerances in the fabrication of these patches. So if there are some error, the resonance frequency will drift this way or that way. So we have decided to design the antenna which has a little more bandwidth as compared to the desired bandwidth. But we can also see that the gain is almost flat over the desired bandwidth, and that is close to about 9 dB. So you can see that these patches are really good, nice, because in this particular case, unlike in the case of planar configuration, where what actually happens that there is a one patch in the planar, another one here and another one here. So there is some phase shift happening because the phase center is at this point. So compared to this patches experiences certain phase delay, but in this case stacked configuration phase center remains same, and that is why the radiation pattern variation over the bandwidth is very small, gain variation over the bandwidth is also very small. One can see that it is almost flat, and this is the radiation pattern. So one can see that E plane, H plane are there, cross polar is slightly less than about 17 to 18 dB. Back radiation we can say is about 15 dB below the front. So we can say that the front to back ratio is approximately 15 dB, and this front to back ratio can be controlled by changing the ground plane size. So instead of 24 centimeter, suppose if we take 30 centimeter, that front to back ratio will be approximately 20 dB. Or the another way is, instead of using a flat plate, one can use a cavity, or you can think about a box. So if you take a cavity like this, then that means the metal plate is really extended in this particular fashion. So back radiation can also be reduced by using that configuration. But for our requirement 15 dB front to back ratio was sufficient, but if you want a more, take larger ground plane or cavity back thing over here. Now this particular antenna had been supplied to the telecom operator and they used this particular thing. In fact, this can handle even 1 kilowatt of power. So generally when people say microstrip antennas cannot handle too much power, which is true, because if we use a thin dielectric substrate, then that cannot handle too much power. But to take care of that power handling problem, what we did, we used 2 thick metallic plate to do the job. Okay. Of course, 2 mm is not necessary, one can use even 1 mm also, and we used a central support which had almost a diameter of 1 centimeter. So, that could support the entire configuration. Instead of that, one can even use 2 different support also, or one can use support at the 4 edges also. That can also be done, but we chose, because I just want to mention, many a times these antennas which are mounted on the top of the tower, they are also required to have a DC ground, so that it provides a path in case there is a lightning. So, center shot does that job also. Now, when you do a center shot, so what happens? Remember, for a rectangular patch, field is precisely 0 at the center. So, you can put a shot over there, but since we put a larger diameter to give a support, so some change in the resonance frequency does occur. So, you need to do that as in the simulation itself, so that you can account for those slightly different changes. One additional thing I want to mention about the plate. Now, in the beginning we thought we will use a copper plate or a brass plate, because then when you are putting a connector from the bottom, that connector center pin can be connected to the top over here. But the brass or copper plate cost is much more, their weight is also more. So, we decided to use aluminum plate. Now, if you use aluminum plate, there is actually a problem. You soldering this coaxial probe, which is of a copper, with the aluminum is not really a very good idea. You can't really solder properly. So, what we decided to do it is, we actually used a brass rivet on top of that. So, that rivet was actually put on the top, and this one went over there and we soldered that. Okay. So, that is the difference, how you can make it a low cost antenna. Okay. So, just by using little simple gimmicks here and there, one can do the thing, and also use the oxidation here. So, you can see that we chose a green color, it is more to do that environment looks little green. Green is always pleasing to more to the eyes, but you can always put any other color also. And also we designed this antenna to have a little higher side frequency also, that in case you need to put that inside a, let us say, a plastic box, or we need to provide a cover to protect from the environment. So, whenever we put a cover, invariably that will reduce the resonance frequency. So, even if the resonance frequency is reduced slightly, it will still cover 890 to 960 megahertz. So, the way we design the antenna, so whether you put a cover or you do not put a cover, it will work in either of the situations. Now, similar thing can be done. I just showed examples of square patches, but you can use a circular patches here, circular patch here, circular ground plane and other thing, depending upon the space or depending upon the place where we need to install these antennas. Now, we will look at another configuration, which is a aperture coupled microstrip antenna. So, let us see what it really is. So, here we have a one ground plane, and in that ground plane, in this particular case here, you can say that a rectangular slot is cut over here. Okay. And other side of the substrate, so there is a dielectric substrate here. So, this is the ground plane, you can think about ground plane of this side substrate. So, that can be a substrate, the metallic portion can still remain there, and one can cut a slot over here. And on the other side, this is the microstrip line feed. Generally, this microstrip feed is again taken for 50 ohm characteristic impedance, and the length of this one here is very critical to decide the coupling between the microstrip line and the above patch. I will just come to that one by one. So, there is a microstrip line here. So, this microstrip line, there is an open end over here. So, that open end would mean current will be close to 0. So, somewhere at a distance of lambda by 4 from the open, current will be maximum. So, it will have a maximum magnetic field. That magnetic field will go through the center, and then it will interact with the patch which is printed on the other substrate. So, for this substrate now there is no ground plane. Okay. So, patch can be again fabricated on the upper side, or it can be fabricated on the lower side, and there can be a gap between the, you can say, between the ground plane and this substrate here, and that can be utilized to increase the bandwidth of the antenna. Again, this patch can be printed on the top side or underneath the substrate also. So, then this substrate will act as a radome for that. So, now let us see what is really happening one more time. So, this is the microstrip line, and generally speaking, this one here, if you look from this side, so this one will be roughly λ/4 extended, so that the maximum coupling can be done through the slot. Now, it is not always necessary that you take that always λ/4. Sometimes if the coupling is too strong to the top patch here, you can either reduce the slot dimension or you can change the length of the microstrip line also. But majority of the time, in order to get better bandwidth, we generally what we do, we use a higher gap over here, so that the patch sees a larger substrate thickness. In this case, it will be dielectric constant and air also, so that fringing fields will be more, and that would give rise to a larger bandwidth. Many a times one more substrate is put on top of that, one more patch is put on top of that, so that will give even more bandwidth. So, here slot dimensions play a very, very important role, not only the dimension, but its shape also. So, in the earlier stages, people had used circular slot here, they also use rectangular slot, and then there were cases where by changing the width of the slot, you can actually change the coupling. So, coupling is more to the top patch if the width is more. In fact, sometimes people had also used this length as a resonant length, but there are disadvantages of that, I will tell you. So, if you use a resonant length of this slot, then that gives another resonance which gets coupled to the other resonances of the patches. It will give overall much larger bandwidth. However, if we choose a resonant length here, then since it is becoming resonant, it also radiates in the back side. So, in fact, one of the major disadvantage of the aperture coupled microstrip antenna is that there is a back radiation, and that is why majority of the aperture coupled microstrip antenna, they have a very poor front to back ratio. And to increase the coupling, many other configurations have been used. So, for example, rectangular shape or H shaped, or even you can think about H shape will be something like this here. You can put a slot over here and a slot over here. So, if you look from this side, it will look like a I shape, but if you look from this side here, it will look like a H shape. Then people had also used a bow tie shaped slot also, dog bone shaped slot also, and then we had studied all these different configurations, and we studied one by one, and then we proposed another configuration which was an hourglass shape configuration, and this actually speaking used the advantages of both H shape, dog bone shape, bow tie shape, and this particular configuration of the slot aperture gave the maximum coupling to the top patches here, and by using that we could get even a much larger bandwidth. So, here the advantages of aperture coupled is it gives very large bandwidth, and there is a design flexibility is there. There are so many design parameters are there. Sometimes it is good, sometimes it is not too good. So, people do not know which one to do and which configuration to use. But design flexibility is that you can optimize this substrate for the best performance of microstrip line. You can use different shapes or the dimensions of the aperture. So, there are a lot of design parameters are there to do the optimization, but the disadvantages are back radiation. So, front to back ratio, as I mentioned, is always going to be poor. It also uses a multi-layer substrate. So, there are so many layers of substrates are there, and the alignment is also a issue. So, these are the problems which are associated with aperture coupled microstrip antenna, and also this substrate here does radiate in the other side because that microstrip line. So in fact they have actually found different solutions also. Sometimes instead of using a microstrip configuration, a strip line configuration is also used, so that the back radiation is reduced significantly, but then that adds one more substrate layer. So the overall cost of the antenna increases, overall thickness of the antenna increases. So depending upon the application to application, so one can use a electromagnetically coupled or one can use aperture coupled. Today we talked about antennas which are stacked on each other. So in the next lecture we will talk about the antenna configurations which uses combination of planar as well as stacked, because we saw in the previous lecture bandwidth can be increased by putting multiple antennas in the same plane. So we have a one patch, put another patch, put another patch, and so on. And today we saw that you can increase the bandwidth by putting one patch on top of the another patch. So in the next lecture we will see we use combination of that. So we go horizontally as well as we go vertically. So we will see in the next lecture how to get even more bandwidth and also little more gain, and yet the performance remains very stable. So we will see you next time. Bye.